Alright. Today, pretty straightforward. Those first two are like a little bit like intermingled. We'll do the light bulb lab for maybe like 5-10 minutes, then we'll do some notes and practice on new stuff. Finish the light bulb lab, take a break, do a partner quiz, then you'll go away. I don't think we'll do electric circuit, but maybe we'll do electric circuit, or electric current, I'm sorry. I'm not really sure. And if anybody wants to squeeze in test corrections before the end of this week, you can squeeze in test corrections today after school. But last time in the light bulb lab, we made a light bulb light up. That was the entire purpose of the lab, was to light up a light bulb. And when we did the light bulb lab, we then kind of looked at this circuit simulator, and we saw that in order to have a light bulb lit up, you could not just take your wire and connect it to the light bulb like so, like we tried to. That didn't work at all. We needed to have a complete closed circuit in order to cause the light bulb to light up. In other words, we had to have the electrons have a complete path all the way around the circuit. Go through the battery, then back through the light bulb, then through the battery, then back through the light bulb, and over and over and over again, until the battery no longer lets the electrons flow. I could have sworn I just saw a person staring at me. I think I might be developing some sort of paranoia, so don't sneak up on me today. It might just be... anyways. So in order to understand what goes on in electric circuits, we're going to constantly draw analogies to things that we can actually visualize. So first off, I want us to somewhat act like we are electrons walking around a circuit. So here are the rules to this. Oh no, John doesn't. The rules are everyone gets a puppy, John. Except for you, because you said no. Right here. So you know what's happening. Then you know what's happening, it's okay. But in your own head, not out loud. Okay. So back here, this is the battery. This is a 1-volt battery. As the electrons pass through the 1-volt battery, you pick up 1 volt of what's called electric potential. As you get that electric potential, as you pass through the battery, you are then excited. In order to show your excitement, put your hands up and walk around the circuit that looks like so.
Like this is great.
Then you get over here. And at this spot right here, at this spot right here, there happens to be a light bulb. And the light bulb serves as a toll booth. I will be standing here acting like a toll booth. If back there, if you get electrical potential at the battery, what do you have to do at a toll booth?
Give it.
You got to give it up. What happens when you drive through a toll booth in your car?
You get money.
You get money when you drive? You give like, yeah, that's a pretty...
No, did I say get?
Yeah.
Oh, I meant you give.
You give money. Electrons do not have easy pass. Nobody try to say that you have electron easy pass. You have to give up the amount of volts that you get back there. Before we do this, let's write down what the loop rule is. And again, after you pass through the toll booth, you're giving up your energy, you're giving up your electric potential, so your hands go down and trudge your way back to the battery. When you get back to the battery, you pick up another volt of electric potential. And you get excited yet again. And you do so until the battery is out of electric potential. Here's the rule before we start this off. Shut up. Here's the rule before we start this off. The loop rule. The rules for electric circuits are the sum of all of the voltages around a circuit, and this is on the front of our lab under pre-lab, which we are doing post-lab, but the sum of all of the voltages around a circuit must be 0. What that means is, if an electron goes through a 9-volt battery, it's got to give up 9 volts before it gets back to the battery. For you walking around the circuit, you're going through a 1-volt battery. On the back of our lab, the top 2 questions. The top one says, what is the purpose of the energy station that was back there? What was the purpose of the energy station that was back there?
To energize.
Energize. To get energy, what are the things that are getting energy in a circuit?
Electrons.
Electrons. So the purpose of the energy station was to give the electrons some energy. The energy station gives energy to the electrons. We'll skip the next part, but then it says, what is this similar to within an electrical circuit? So that energy station back there that gave the energy to the electrons, what's that similar to in an electric circuit? Battery. So within an electric circuit, the battery is given energy to the electrons. We'll come back to the up escalator thing. But if we kind of skip down to the next one, what was the purpose of the toll booth? Purpose of the toll booth is to take energy away. What was that similar to in an electric circuit? Light bulb. Or microwave. Or television. Or hair dryer. Or phone energizer. Or whatever you got plugged in the wall. So whatever's actually being used, whatever's actually being powered, that's what the toll booth is similar to. It's taking the energy away. So the electrons are just kind of carrying the energy around the circuit. If we kind of zoom in here and take a look at our favorite electron, find your favorite electron.
Okay.
Which one?
That one.
This one?
Yep.
How did I know this again?
You're just that good.
Okay, so this one?
Yeah.
All right, sounds good. So we're going to follow this electron around its journey. Ready?
Yeah.
The electron's going around its journey. It's not very energized right now. Then it's going through the battery. Whoa! Whoa!
Oh,
Whoa! The electron got some energy from the battery. The electron is very energized. It got energy from the battery. It is carrying the energy. The electron is so energized, it has so much energy, and then it hits the light bulb. What does it do to the energy?
take it.
Gives it up. The electron gives the energy to the light bulb. So what does the light bulb do?
Shine.
Lights up. If the electrons weren't carrying energy to the light bulb wouldn't shine up. So the electron's just carrying energy from the battery to the light bulb. Then once it gave its energy up, it's getting pushed by ones behind it, so it continues around the circuit. There's two questions. How is it similar to escalators? I don't want to try to push that analogy, so we're not going to. So you can kind of take the lab and put the lab off to the side for now, and it says, stop, notes on potential and potential energy. Okay. There you go. You're welcome. There you go.
Beside the table.
This is a 6-volt battery.
Oh my god, we were just talking about those.
6-volt batteries?
Yeah,
those
big-
things.
Oh, yeah.
Freaking like
Those freaking old brick bags.
These things are great. So this is a 6-volt battery. Back there I have a 9-volt battery hiding somewhere. Has anybody ever licked a 9-volt battery?
No. We
Okay.
did.
So they did, because I made them when they were in here the other day. But when you lick a 9-volt battery, what do you feel happen?
A little buzz in your tongue.
Vestigo said he feels some brain cells dying. I don't know if that's necessarily true.
Like a
Survival of the fittest, man. So when you feel it, you kind of feel like a zap in your tongue.
Like a tingling buzz.
Now, if you kind of figure that you're replacing this light bulb
just like that.
with your tongue. So I'm going to put your tongue here, just connecting that together. What you feel is you feel the volts, you feel the electric potential, you feel the energy going through your tongue and then back to the battery, and then through your tongue and then back to the battery. And if nobody's ever licked a 9-volt battery, I'm not going to suggest that you go lick a 9-volt battery. But not saying anything. But you actually feel the electricity, you feel the energy going from one side to the other. Now, those are 9-volt batteries. This is a 6-volt battery. Those little like C, D, AA, triple batteries, AA, AAA, C, and D, those are 1.5 volt batteries. What a volt is a unit that's called, or a measure of something called electric potential. And what electric potential is, all electric potential is just the energy that a charge has divided by how much charge it has. The first letter in electric potential is V. So this is electric potential. Electric potential, sometimes it's called electric potential difference. So I'll write that up there as well. Electric potential or electric potential difference has the symbol of V. The first letter in energy is
W.
W. Why is W the first letter in energy? What type of energy starts with W?
Work.
Work. So if you actually look on, flip the electricity portion of your reference table quickly and bust out a reference table if you don't have one yet.
Bunch of
On the right-hand side of the electricity portion of the reference table, it says W, and then I think it says work, and then in parentheses, electrical energy. So W means work, and work is a form of energy. First letter in charge is
Q.
Q. So Q represents the charge. So this is the first equation all year long where none of the letters have actually been the first letter in the equation, which is a little bit strange. But in terms of the units for all the things up here, what would the unit of energy be?
Joules.
Joules. What would the unit for charge be?
C.
Coulombs. So the unit for V would be
Joule.
joules per coulomb. But we don't feel like saying joules per coulomb over and over again, so we simplify joules per coulomb, and we give electric potential the unit of a volt.
bless you.
Bless you. So this V stands for electric potential, and the unit for it is V, the volt. So V, just keep that in mind.
V.